Okay, good morning and welcome to the Space4Cities Phase 2 Demo Day. And this is the first day of a series of two, so today and tomorrow, where we are presenting some exciting updates from our Space4Cities projects, especially what the 10 suppliers that we've been working with have been doing over the past 6 months. Just as a note, this meeting will be recorded for people who couldn't join the meeting, and as such, obviously, it also provides an opportunity later to come back to some of the talks and catch up with the things maybe that you might have more interest in. Okay. So my name is Alex Gluhak. I work for Open Inata Smart Cities, which is a smart city network. We have over 200 members working together. We are a partner of Space4Cities as well. In Space4Cities, we are leading on the capacity building activities and also on the replication call, which I will talk about this in a minute. Just maybe to set a scene, we have a few things about the project. So Space4Cities is a pre-commercial procurement activity funded by the European Union and specifically by USPA, so the EU Agency for Space Program. And it brings together 7 consortium partners. 5 of them are cities and regions, but also others like networks like us, city network, or also like a supplier network such as Aerospace Valley, to work towards adoption of space-based solutions that can make a difference to challenges that cities and regions are facing. And the project started already, 2.5 years ago, it seems. Really our idea is to stimulate now innovations in this space. So innovations that leverage space data and space technologies, particularly European space data and space technologies, to develop solutions, novel solutions that respond to challenges that our cities are facing. And the idea is that it's a multi-stage procurement exercise where we are procuring innovations from the market and then are piloting those as well. And we are sort of soon also entering this pilot stage, which is quite exciting. And before we do that, obviously, it's a good moment now to share what our suppliers have been doing. Generally, the overall project focused on urban challenges in 3 areas. One around sustainable mobility, the other one around climate adaptation and resilience, and the third one on urban planning and management. And within those different areas, our cities in the consortiums defined together also with a wider network of cities, specific use cases and challenges that could be useful for adoption of space technologies, or where we see space technologies or space database technologies can actually deliver real benefits to the cities. And what we did is we sort of put those challenges out to the market and also the specific use cases that we had in mind. And then we ran a large procurement activity, which took place last year, the beginning of last year, where we had a really, really great response. So 150 nearly solution providers and consortia responding to it, out of which we selected 20 for initial solution design phase. Out of those 20, we then selected 10 suppliers to develop the solutions further. And these are the 10 that we will be showing now over the next 2 days, so today and tomorrow. And finally, 5 of those that you will see over the next 2 days will be actually selected to actually actively pilot the solutions in our cities. And more importantly as well, not just the 5 cities that we have, but also additional replicator cities. And obviously the idea really of those events that we are organizing now is to prepare as well interested cities and regions to join some of those replication pilots. So the 10 solutions that we have can be categorized broadly in sort of different themes. They cover areas such as structural health monitoring, water leak detection, emission management, urban green space management, climate risk management, wildfire management. And obviously, these are broad buckets that I put them. Some do slightly more, but I think that's sort of a good mental model for you to keep. And today we will be actually hearing about the first top 3 here on this list. So we'll have basically the teams behind presenting like the solution prototypes they've developed as part of this last 6 months. So basically the phase 2 of SPACE4Cities. Before we sort of dive into these presentations, there's a brief reminder as well that we are obviously looking for replicator cities and regions to join our endeavor. Basically, in the following weeks and months, we will select 5 of those solutions to be piloted in 5 of our different cities, so 1 each. And we will basically invite them through an open call, other cities and regions to join us to also replicate the solutions in their city environments. So now is really a good moment for you to understand what those solutions are. Obviously, I can't promise that you will see all of the 10. It will be 5 just of those. But I hope you will still have an interest in engaging with us. And we will be obviously supporting you. The pilot costs will be covered from the supplier side through our procurement. And you will also receive some smaller support for travel or that is potentially needed to exchange experiences, visit a pilot city, for example, a main pilot city, for example, and so on. And this will be launched in like the next 5 weeks, this call. And just sort of as a reminder of the timeline, so in July, we will launch this replicator call. You have roughly until the end of summer, so September, to respond. So there's going to be like July, August as an opportunity to put in an application. And this is a very lightweight application, I promise. And then we will select basically 2 additional cities per pilot, so 10 overall, to also further test and trial the solutions that you will hear about today. Okay, so before moving on, this is basically the overview and the running order of today. I know it's a very sort of dense schedule, so it's a 3-hour slot. We obviously don't expect you to be there for all of the time, but if you want, that would be very appreciated. Otherwise, you might also want to drop in maybe for the slot that's most of interest to you. So you've got both options here, right? But I think what people have done, and if you can afford the time, I think it's really worthwhile staying and being part of the entire session today. And a similar session will also run tomorrow, right, for the other 5 groups. So we will have basically CityMotion first with Candela, then GeoRisk Monitor later with Radar, CHERISH with both Daniel and Yanis, then Urban Lens with Denise, and then DYNAMO-SM with the Ever Impact team. So say Lorenzo, I guess, will be part of the story, and potentially Mathieu. Okay, and then the idea really is that we'll have these talks, so there will be hopefully also some live demos, let's see, depending on what the different suppliers have chosen. And then you'll have basically a brief Q&A after the talk as well, like an opportunity to ask questions. The idea is like 5 minutes or so, and then we will switch over to the next talk. So there's maybe a little buffer between the Q&A and the next talk, right, of a few minutes. So for maybe a comfort break or something like this. Okay. So maybe a few housekeeping rules. Obviously, this is like a webinar. We want obviously the speakers to have the full attention. So please turn off your camera when you're not basically when the speakers are presenting. Later in the Q&A, you can interact, right? So you can obviously raise your hand. You can we can get you in, or you can also post your questions via direct messages into the chat, and we'll keep an eye on those and bring them also into the conversation then. Okay. So with that, I think I will leave it there, and then I will hand over to our first speaker today, which is Candela.
Thank you very much, Alex, and I will share. Let's have a bit of everything. First 5 minutes of PPT, and then we will go to the demo. So hello everyone, my name is Candela from Detectia, and together with my colleague Alvaro, we will show you the CityMotion prototype we have developed during SPACE4Cities. So today, cities have access to an ever-growing volume of insert data. So the challenge is no longer collecting data, it is turning it into clear, actionable answers. So insert can generate hundreds of thousands of deformation time series across a city with millimetric precision. But in practice, this level of complexity makes the data very difficult to use. So city managers are not looking for raw data. They need simple answers. When did something change? Where did it happen? And how big was it? So CityMotion was created to bridge this gap. So transforming complex geospatial data into intuitive decision-ready insight through AI and natural language interaction. So this is a summary of Detectia's technology before SPACE4Cities. So Detectia provides advanced tools to analyze large volumes of deformation data delivered through our API. And this API is mature and highly flexible. So it allows deformation to be decomposed along user-defined axes, detects anomalies and changes in deformation trends over time. It also analyzes how external variables such as temperature or rainfall influence the deformation behavior. So it also calculates aggregated structural health metrics for any asset in the city. So the wide range of spatial and temporal analysis tools available in our API makes it very powerful, but also complex to use. So using it efficiently requires a specific expertise in satellite radar technology and geospatial data analysis. So this can become a barrier when trying to extract valuable insight from such large volumes of data. So this challenge is exactly what we address by adding a new component to our workflow. And this is the focus of our work within the SPACE4Cities project. So we are adding large language models and intelligent agents that allow city managers to use complex geospatial tools through simple natural language interaction. So this is the core idea behind our innovations in this project, combining the power of Detectia's advanced API with the simplicity and accessibility of large language models. In this way, overwhelming volumes of geospatial data are transformed into intuitive and accessible insight that can be used by city managers in their daily work. So CityMotion is built around two complementary pillars. So first, it exposes full capabilities through an MCP that enables seamless interoperability with AI agents and large language models such as ChatGPT, Claude, or Mistral. So this allows external tools and platforms so they can securely access advanced geospatial analytics and combine them with other data sources. As AI becomes central to the future software, this ensures CityMotion can integrate natively into next generation of GIS, BMN, and digital twin ecosystem. And second, CityMotion is also delivered as a complete and user-ready web application. It provides city teams with maps, dashboards, and conversational interaction in a single interface, allowing them to directly explore deformation data without relying on external systems. And this is important. This web application is itself powered by the same MCP layer, making it a direct example of how CityMotion can be integrated into any AI-enabled environment. So we are moved into the demo. So first we will see how this MCP works. We have decided to go for Claude, and then we will see the web app. So I will now share, I think I need to share my entire screen. So 1 second. Share again. Okay. So I think you can all Should you see my screen now? So this is CityMotion in Cloud. So the first thing we want to know is like, okay, we can see in this connector, we are already connected to CityMotion. And so the first thing I want to see is like, okay, what information is available on CityMotion? And now through all the different tools of the MCP, we are going into the catalog. And this is the answer. Here's a summary of what's available. We have urban ground deformation data derived from INSAR, and it covers 5 cities. So these are the 5 cities. And this is the type of data you have for every city. You have points, with the movements in planimetry and in vertical, which each data points has velocity, has a model. We have modeled the time series, so we can see how big is the influence of precipitation, temperature, how is the trend, if there is any jump, any trend, something that happened. And we have data over the polygon. So what can we do? So now let's start with the first city, for instance. Let's go to CHERISH. So I will say, okay, I want to analyze the deformation data in vertical. What are subsidences? I'm interested in the city of CHERISH. And now through the MCP, we are calling to the different tools. So okay, let me get the properties. And you can see it is calling all the tools. Let me get the model data and the data. Well, it's looking, okay, I will allow. It's looking at I didn't say points, so the model is looking both for the points and for the polygons. Okay, so now we are getting the explanation. Let's see what we get. Loading the information data. Yeah. Okay. Here's what it says. Okay. We have calculated all the metrics through 19 time steps over a period of 5 years. So yeah, please, but okay. Sorry, I didn't specify buildings or points, so it's analyzing all the data sets and all the information that it has on the database. I don't see, yeah, Alex, I don't see if there is any question for us, and I think there are.
Yeah, it was just about the recording, so don't worry about this. Yeah. So
Okay.
we will take them anyway. But obviously, as you're waiting, maybe it could be a good moment as well. Yeah.
Yeah. Okay. Here you have the summary. Okay. So there are data layers for CHERISH deformation, point velocity, kinematic model, buildings. Okay, I should rephrase my question better. And write it better. I want to analyze the formation data points in vertical in the city of CHERISH. Let's see if now that I say points, is it like okay.
So what happened just now? Kind of like, can you just say a few words? Why did he now deliver something else than you expected?
Because I didn't say whether I was interested. At the beginning, he told us, I have points and I have polygons. And I say, I want to see vertical, but he was asking, okay, but you have points, you have buildings.
Yeah,
so let me see. This is a summary. There are 3 layers that are ready. Point velocity, all the modeling of the velocities and the polygons. Which one would you like to see? And I said, okay, points is the information that I forgot to introduce, points. So now it says, okay, we have 30,735 points in the city. That moving is over 1,000 points, 16% of the points. With significant subsidence, with a threshold lower than 2 millimeters per year, we have 900. So stable are 25,000. And we can see with a strong subsidence, we have 460 millimeters. So we can now go to see, for instance, all the points. And we have all the points within the city with the average velocity. But I'm not interested in this map because I just want to see the ones with significant subsidence. So I'm going to open them. And now I can see I don't have that many points, but still there are quite a lot. So I can say I am interested in the points with subsidences larger than 10 millimeters. So now, because I still have 460 points, so I'm interested in seeing which are the points that are moving a lot. See, oh, again, this is negative, so I forgot to minus 10 millimeters per year. And it says there are no points that has a velocity larger than this one. So this is an example. And for instance, for the previous one, let's go back to the map. So we can see this area, how are the time series. So here we can see the time series of INSAR is this light gray time series, and we have modeled the time series. So in order, we have the temperature that doesn't influence a lot in this model. So in order to be able to model time series, there is a jump in the model. So we can see how this jump occurs in the different moments. That means something has happened that it is needed to introduce this change, this jump. But this is enough for let's say, I need to close all these tabs. Well, you can see now CityMotion, right? So let's go to the next example. This is our web platform. And you can see we have data in these cities. This data is here, and we have our agents. So if we click in a city, for instance, let's go to the Netherlands, we can see the agent is starting to work, and he will show you what is the information that is available in this city. Wow. In this case, we have processed the area that is in this line. Okay, so I have the information. Here, do you want to analyze data? We have the information planimetry, vertical, breakpoints, thermal response, building level comparison. So what you would like to see. So I can include the velocity here by hand, but I will ask the agent to do that. So I want to see on the map the vertical deformation velocity in the area on the Wallen. There is an area in Amsterdam. So let's see if we have the deformation. It's geocoding. So first it's looking for where is the Wallen, and now it's looking for the data we have in this neighborhood. Okay. So the velocity layer is visible on the map. So we can see all green velocities because the scale is really large. Let's say movement subsidences larger than 5 millimeters, red, absidences in color in blue color. So we can see we have red points with the break jump and the model, and maybe we can see, okay, but now I do not want to look at the time series at this moment of the points. Let's take a look. Let's take a look at the vertical building deformation metrics for this area in Amsterdam. So I will draw a polygon. So it will be like really fast to extract the metrics of this area.
So while you're sort of waiting, there was a question actually, which was by Hui Biao, and he asked basically, what's the advantage of using an LLM rather than any query language? So, because obviously what you're just demonstrating are like queries or GeoRisk queries. What could an LLM? Why is an LLM useful for this as compared to, let's say, writing your own sort of geospatial query interface?
Well, maybe Álvaro is the person to answer this
Sure.
question.
Yes, I think Candela, this is easier for any user. That's the main advantage. Apart from this, the LLM can do if the LLM can access, well, the agent can access all the tools. Maybe he can do analysis that are difficult for. Yes.
I mean, we are not all IT experts. So even though in the Tectia we use an API, I don't know how to connect to an API. Álvaro does because he's our technical person, but I'm an expert analyzing the information. And I have no idea how to connect to an API. So it's just easier. You just use natural language. That's the big thing about it. And well, meanwhile, I will continue. Maybe we can keep talking about it later. So this is the results. Now let's hide the points. So we have the metrics. I will remove this as well. And now we can see, for instance, we have this red polygon, and we can see how the metric changes through time. Since in 2019, when we started our analysis, everything was stable, and we can go through time how all the different blocks are moving, and we can start analyzing when the formation started to accelerate or when did something happen. And we also have the differential movement. We know if a building might collapse or might have cracks because it have different movements within the city, or if the entire building is sinking or is moving as an entire building. And then we can click in this other point, and we can see the time series of all the points in this band. Light band, we have all the points that belong to that building. As would you like me to interpret? Yes, please. So I don't need to be an expert because I get support to see the data, the metrics, and all the information, and also how to interpret the time series. Even though if I'm not an expert, here I have the support. So within a couple of seconds, we will have the answer. So this is a sub-agent that we have developed that is interpreting, according to the knowledge we have done to this agent, is interpreting the time series. And here say, so you have two different building deformation behaviors. First building, 160, is the one in this purple color. There is a sharp downward around late 2019, about 1 centimeter. It continues moving downward. By 2023 has reached more than 3 centimeters. This is the main concerning signal and should be validated. The other building in 203 in yellow colors is more stable, early fluctuation, no major abrupt jumps. So the most important feature, because of this jump is large and follow a continuous subsidence, this building should be treated as a priority for further inspection or validation. So this way we can analyze and have an idea and a list of how all the buildings and infrastructure in my city, which is the state and which need to be prioritized for maintenance or not, or which ones are stable. And let's go to another example. Let's go back to CityMotion. And well, just say if we also have a tutorial, so explaining all the panels and all the steps, and just another easy example to start with. We will go to Finland. So in Finland, we have this data, and I will select a small area so we can do it very, very fast. I will select this area with bridges, and I will say, I want to analyze the contribution of the temperature in vertical point deformation. Because I know bridges, they have a thermal response. So let's say I'm interested in see how are the thermal response and the deformation in my bridges. So it's a large area. I confirm I want to analyze this one. So we are working in this area where we have points. So we are getting the kinematic variable. So within a couple of seconds, we will have the information. Okay, so it says this is the vertical temperature contribution. So I know how much temperature is affecting my data. So I can see, as I was expecting, there's a large contribution on temperature over bridges. So let me click on this point. And we see how is the insert data in this dark line and how is the model taking into account the contribution of the temperature. And now I will to see, okay, but I have a lot of points. Let's filter the points with a temperature-dependent deformation coefficient greater than 0.25 or less than minus 0.25, because you can see here on the line, it says it goes on to 0.5. So let's take just the extreme points and see how much points we have with this large contribution. And we can see the points with large contribution are less. And I could say, I would like to display these points on the map, colored to color according to their velocity. Okay. And now instead of color the points but how is the correlation with temperature, I will plot them by the average velocity they have. In the vertical velocity, okay, so out of the 4,000 points, we have only 100 points, and I plot them. Let me check the color. I plot them by the average velocity. We can see these points on the bridge are in green color. They are quite stable, but we have 3 points here with a large subsidence velocity. So you can see these ones with the largest temperature coefficient, they are kind of stable. It's just seasonal behavior. But here we have these 3 points that have really a large subsidence of 1 centimeter per year. So this is a nice way to analyze out of the more than 4,000 points, which are the ones that really need inspection or where something is happening. So yes, help me to interpret. And here we have the interpretation of these points that I have selected.
Candela, just a note that maybe 1 more minute, and then if possible, then we can maybe have some questions still before the next speaker comes. Okay.
Yeah, I was not planning to ask anything else to the agent, so
No, it's fine.
I'm all over yours. Here we have the interpretation, what we have done, temperature, 100 points, how to interpret the velocity colors, and most important interpretations, and engineering interpretations, and recommended. So, you know, I'm all yours. This was the demonstration we have prepared for today.
Brilliant. Thank you so much. And it's always so brave to do a live demo. Yeah, well done. So really good to see this, Candela. Okay, so we've obviously we have a bit of time now for questions. I don't know, Biao, did this answer your question now? That Candela said why an LLM is an advantage. I think the sort of second part of the demo hopefully made it a bit more clearer. You okay with this? Okay. There's another question, Candela, coming. I don't know if you can read it. If you want, I can read it out loud. Do you have
Yeah.
any method to mitigate the hallucinations from LLM?
Yes, this was the big challenge we faced at the beginning of phase 2. Because, well, I will explain it in a not technical way, and then Alvaro is here, so he can correct me and put all the technical words. But let's say we put all the information to the LLM, and then it was too much information. But then we decided to do, well, maybe Alvaro, you can explain it better because I don't even know how to explain it in few words.
Yes, I think there are two components. One component is that now what Candela is saying is at the beginning, we didn't manage the context properly. And everything, data, the questions and the prompt were into the context, and that was a lot. And the agent could make up data results. Now it cannot because all the data is not exposed to the agent, but is stored in very fast drives that the agent can access but not see. So the agent is focused on just the analytical tools that we provide them. That is the other part. Instead of allowing the agent performing random analysis, the agent can use only those tools that we provide through the MCP. So this is why we have tools that have been tested by us, and at the same time, no raw data goes to the context.
Yeah, so we become this a very deterministic process because, as Alvar said, we are just calling tools that we control, and these are the only tools the agent is able to use.
Yes, and here, if I may come back to the previous question, yeah, before we didn't have time, sorry, Candela, it was a very long explanation from my side. I wanted to say that this is what also gives us an advantage of using agents. The agents know all the tools that are available. There's no need for the user to know all the things that can be done. And it's not just queries. I mean, we can query, the agent can interpret the data as we have seen, and also via suggestions or via, I don't know, maybe the model is creative this day and decides to use many tools in a row. So just asking like, okay, I want to analyze subsidence is not a query of, okay, I want to see the velocities. It's a prompt that might cause that the agent downloads the data, filters the data, displays the data, maybe also gets the polygons and show you everything and wrap up with a nice, I don't know, explanation at the end. So there are a lot of advantages.
Perfect.
Yeah, and yeah, the last thing, we have traceability on it. So we know what the agent has done, all the tools, as Alvaro said, that it has called. So we know and we have validated what the agent is doing.
Perfect. Okay, I think that's great. So thanks really for your also demo again, the great explanations. I think we are unfortunately like having to jump now into the next, or fortunately, but we have to move on to the next one. And obviously there will be another opportunity at the very end to interact, guys, still. Okay, so I will now hand over the presentation to Reda. He will present the GeoRisk Monitor project. Reda, the floor is yours now. Okay. And by the way, you're still muted, I think. So just, you know.
Yeah, I think I'm live.
Yes, now we can hear you. Very good. And we can't see though yet.
You should see a black screen, right?
Yeah, black screen. Yeah, it's true. There's some word thingy.
Now,
Yeah.
now you see the magic.
We can see it. Thank you.
All right. Hi, good morning, everyone, and thank you for being here. My name is Reda, and I'm going to present GeoRisk Monitor. It's a predictive maintenance tool that we have developed especially for cities. Here's a picture of a city asset management team. Why do they look so stressed? You might be wondering. Well, did the manager tell them that they had to sit through this presentation? Nope, they don't have time for presentations. They're too busy trying to stop the city from literally falling apart. Every day, they're juggling with roads, bridges, tunnels, quays, levees, basically everything people complain about the moment it breaks. The job keeps getting harder because most of these assets were built decades ago, and we are now reaching the end of their lifespan. Traffic is increasing, vehicles are getting heavier, climate change is adding its own special charm, excessive rain one month, drought the next. And just when you'd expect budgets to increase, budgets get cut. Because politicians love cutting ribbons and shiny new infrastructure. And nobody ever wins votes by proudly announcing, "Good news, everyone, the roads are still functioning." So how can we help you? Can we increase your budget? No, I'm not a tech billionaire yet. But what we can do is help you get the maximum value out of the budget you already have. GeoRisk Monitor is basically an early warning system for infrastructure. It helps cities spot problems before they become front page news. We've seen that cities using GeoRisk Monitor can identify risks 12 to 24 months earlier. And in infrastructure terms, that's the difference between let's schedule maintenance next year and why is there suddenly a sinkhole swallowing cars? True story, by the way. That extra time matters. It gives cities the chance to make a proper remediation plan, budget for it, and fix problems calmly and safely. And most importantly, it avoids expensive emergency repairs. You know the kind, where everything suddenly costs 3 times more because it has to be fixed immediately, at night, in the rain, with angry citizens filming and posting on social media. GeoRisk Monitor helps cities move from reactive to proactive. Instead of waiting for infrastructure to fail dramatically, you intervene early when action is still cheap, safe, and boring. Now we get to the technical stuff. And don't worry, I'll keep it to an absolute minimum. What GeoRisk Monitor does is transform satellite data into geological insights. Or in plain English, we use satellite data to figure out what the ground is doing before your infrastructure starts complaining about it. We take Insta satellite data, which basically measures tiny ground movements, and we reprocess it into 3D geological deformation models. Yes, there's a lot of calculation involved. That sounds very impressive, because it is impressive. But the important part is this. We're not just measuring that the ground is moving. The ground has always moved. That's geology for you. The real question is this movement actually a problem for my infrastructure? Because a few millimeters of homogeneous movement, nobody should care. But a few millimeters of differential movement, everybody should very much care. So instead of giving cities another colorful map with dots moving up and down, GeoRisk Monitor shows where geological forces are actually creating risk for infrastructure. Where are the tensions building up? Where are structures under stress? Where should you inspect before something expensive and embarrassing happens? Based on the geological forces, we calculate strain. And strain is basically the precursor to damage. It is the stage before cracks and before failures. The challenge for cities is that this whole process is invisible. Infrastructure doesn't wake up one morning and announce, "Good morning, I am now structurally compromised." Strain develops slowly, underground, over time, often accelerated by climate change. And that's exactly what GeoRisk Monitor makes visible to you. At one glance, we show where risks are developing today and where future damage is likely to appear tomorrow. So instead of reacting when something breaks, you can see where the pressure is building and act before the real problem starts. And now that we've talked about the technology, let's show you what it actually looks like in practice. This is the first thing a manager sees in GeoRisk Monitor, all infrastructure risks at a glance. Every asset is shown on the map: roads, bridges, quays, public buildings, tramways. And we keep the color system very simple, traffic light style. Green means low risk, orange means medium risk, and red means, you guess it, high risk. And on the left side, all assets are automatically ranked by risk from top to bottom. So instead of spending weeks figuring out where to look, cities immediately know what needs attention first. Because if everything feels urgent, prioritization becomes the real issue. Asset managers are usually responsible for one specific asset class. So here we zoom in one specific asset type, roads. The platform immediately shows all roads on the map, again, with the same color coding for risks. And now on the left, the list is different. It's focused on the roads. The roads are automatically ranked by priority again, based on that strain score I talked about. So instead of inspecting roads one by one, or waiting for complaints from citizens on social media, the city can immediately see which roads are stable, which roads need inspection, and which roads should probably move to the top of the maintenance list. It turns infrastructure management into data-driven prioritization. Of course, users can select any asset type from the list: roads, bridges, tramways, quays, whatever is relevant for the city. And the asset list itself can be completely customized. We can create different asset classes and subclasses depending on how the city already manages its infrastructure. In this example, we select quays. On the left side, we see that KA is on the top of the priority list. So instead of searching through all the quays, we can immediately focus on the quay that matters most to us at this moment. KA is at the top of the priority list because it had the highest strain score. So naturally, we want to zoom in and understand why. The strain score is calculated using 6 different stress indicators, shown here on the left. These indicators are based on decades of geoscience expertise and more than 10 years of experience interpreting INSAR satellite data. The time series for the EGMS server are far, far away from what we are capable to do today. And this is where GeoRisk Monitor is fundamentally different from most existing tools. Most tools only show movement, but movement alone doesn't tell you whether infrastructure is actually at risk. What matters are the forces acting on the structure. For example, when the soil moves and the structure resists that movement, stress starts to build up. And when that stress exceeds what the structure can handle, you get strain. Strain is what eventually leads to cracks, deformation, and failure. We increase the spatial resolution to 10 by 10 meters, so you can see exactly which part of the quay are vulnerable. As you can see, it's not the entire quay that is under pressure. There is one specific section of the canal embankment with a high strain value. And instead of averaging the risk across the whole structure, GeoRisk Monitor pinpoints the exact location of the maximum strain. We could go deeper in the analysis, and geotechnical experts and engineers may want to look at the individual stress indicators in more detail. Is that possible? Yes, absolutely. For every single point on the map, we have access to the underlying stress factors that contribute to the overall strain score. So let's take the vertical velocity as an example in the box. This is actually what most competing solutions focus on, vertical ground movement. We display the vertical velocity across the quay. On the left, you see the full distribution, from -5 millimeters per year to +5 millimeters per year. And on the right, you see the value for the selected cell. Why are we interested in that cell? Well, we're interested in all the cells, so why not that one? This one is -1.2 millimeters per year, 1.19. Okay, so what's happening in this selected location? Interestingly, it is not where the maximum vertical movement occurs. That's actually the dark red spot further away on the map. In this spot, the vertical velocity is not critical. Does that mean this section of the K is perfectly fine? Apparently so, but not necessarily. And that's exactly the limitation of looking only at vertical or horizontal movement, because infrastructure damage is not caused by velocity alone. What really matters is how a network of different forces interact and where stress starts accumulating inside the structure. When we look at all the stress indicators together, the 6 of them, we see something interesting. The vertical and horizontal velocities are actually not very alarming in that specific location. They're both relatively close to 0, which is the middle of the color bar. So based on movement alone, this area would probably not stand out. But 3 other stress indicators are showing elevated values: low stress, left and right. So on the right of the color bar, you see low stress, and on the right of the color bar is the high stress to understand the color and the values. One of them is even the critical range. If you see my cursor, I point towards the one. This is exactly why looking only at movement can be misleading. The real risk only becomes visible when you combine all the stress factors together. But of course, CT don't only look at the assets with the very high strain scores. Sometimes there are other reasons to focus on a specific location. For example, maybe a renovation project is already planned, or the K is part of strategically important traffic route that we need to keep safe. So let's take a closer look at the city-defined priority for the Ks in Zone B. Even though it's less urgent according to the main stress score and the list on the left, the platform still allows the city to quickly investigate the local conditions and understand whether additional risks are developing for the future. And to put it plainly, just understand what's going on. 2Ks in Zone B show a completely different behavior pattern because there's probably different geological model deformation at play. And that's exactly where the stress indicators become valuable for engineers. They can see this detail. It helps them understand what kind of forces are affecting the structure. It gives them clues on the deformations at play and how to design the right remediation strategy. In many ways, the stress indicators provide information similar to what you would get from physical sensors installed on site. And if additional inspections or monitoring are needed, GeoRisk Monitor helps cities decide exactly where to place those sensors and where to focus on site investigations. This is really the big picture, the long-term impact of using GeoRisk Monitor. I'll give you a few seconds to read it yourselves. At the end of the day, infrastructure is not just concrete and steel. It's the roads people drive on, the bridges people cross, the levees communities rely on for safety. Our goal is simple: to help you optimize your budget, intervene earlier, reduce risk, and keep infrastructure safe for everyone. We're back to the same asset management team. We see that they look happier, and not because infrastructure suddenly became easy, and definitely not because politicians doubled the maintenance budget overnight. They're happier because they finally have visibility. They know where the risks are, what needs attention first. and where they can intervene before problems become crisis. Less firefighting, fewer surprises, better planning. And now is the time for your questions.
Okay, Reda, thank you. I think you were it's quite clear presentation, right? Thank you. A very good storyline. I think we're a bit ahead of time actually. So you have a bit more time. So do you want to maybe also take this to maybe show your tool or live, or do you want to, you know, because obviously we will have otherwise a gap in the program. So compared to the next speaker.
I was expecting questions, and
Oh, sure.
I prepared some times for the questions.
Yeah, that's okay. So yeah, so maybe we can ask the audience a little bit more. Are there any questions for Reda? You can obviously just raise your hand briefly, or just turn on your mic and ask a question, or drop it in the chat window, whatever you prefer.
Or maybe it was so clear that everybody wants to use it straight away.
Perfect. Yeah, Michaela, if you don't mind, yeah.
Do you hear me? Good morning. Thank you very much. Thank you very much for this very nice presentation. I have a question that is not directly related with the presentation, but with the data you showed and you used for risk assessment. I just would like to know if the approach you used can integrate other kind of data, like some data that were presented before in for the city movement, CityMotion, sorry. Since, for example, probably some, I think I am not an architect or an engineer, but what you show only very few parameters, and I think, for example, the temperature, surface temperature, can have an impact on this kind of assessments to some point, I imagine.
Yes, absolutely. So the impact is already recorded in the time series, the displacement time series. So this is taken into account. But what matters is that the temperature itself doesn't matter anymore. It's imprint in a time series, which is recorded. That is the part that we use. So if that time series is affected, then it is recorded and we take it into account, where we defined possible stress, possible different behavior. We actually recreate new time series of geological modeling that answer for compression, extension, shear, deformation, and we always check the coherence with the neighboring values. So all that is taken into account, and also the variations through time. Is the time series very continuous through time, or does it show big anomalies and change of trends? This is also taken into account. This is why we have 6 stresses. They are based on anomaly displacement, the differential displacement. They are based on anomaly of acceleration with coherence spatially with the neighbors and coherence through times. And that makes for the 6 stress indicators that are concatenated together to show some sort of maximum strain condition when all stresses point to the maximum, and minimum strain conditions when all the stresses point to the minimum. So to answer your question, we also deliver data. So for every location, every 10 by 10 meter, there's a time series of deformation, and the reporting through PDF form of the strain analysis, strain sorting to understand the priority areas, and of course in a form of shapefile and GeoJSON file when the data needs to be integrated into GIS platforms.
So Michaela, did it answer your question?
Thank you, thank you. Yeah, actually, I imagine that that those data include the causes, for example, the temperature. I was just wondering if can be provided a more in a more explicit way the link with the cause. This because okay in
this is the answer is in the geological model. You see, when the temperature changes, it affects, for example, the water content in the ground, and that modifies the mechanical properties of the ground. So it is integrated in the geological model. When the geological properties are changed, then the ground behaves differently through time, and that behavior is recorded.
So I think the point is, Reda, your model implicitly considers it, the temperature.
Yes.
But I think Michaela has also an interest in her question whether also explicitly such relationships could be modeled, right? So whether you could get also data that sort of like outside your indicators that are explicit, like temperature. So you could also kind of understand the influence, right, of those parameters. Is this correct, Michaela? Yeah. So
absolutely. I have in mind the climate change, increase of temperature, of precipitation, of extreme precipitation, and if this relation is more clear, then it will be not more easy, but plausible.
Yes, yes. The solution is very, very clear, very evident. The both areas should match. Yes.
Perfect. Good. Thank you, Michaela, also for the question. So
thank you.
Yeah. Do we have anyone else in the audience? I think there was actually a post here. Very good. Thank you. I can read it out. So first of all, it says, congratulations, very good presentation. While this pilot can be applied literally to any location, which are the candidate pilot cities for this demo, and which additional cities would you consider to be relevant to introduce the pilot at this stage?
The answer is yes, it can be applied anywhere because it's completely agnostic to climate, geology, and type of infrastructure. So it works everywhere. Now it can be applied anywhere. It's just a matter of the deciding who wants to apply it, who is interested, and who would make contact.
Brilliant. So this means you don't have actually any local data dependencies. Everything is available through the INSAR data and obviously your models. Can we say that?
Yes, we can enrich the INSAR data with any external information. So depending on which city, whatever they want to share can be used to increase the accuracy. But only using INSAR data is the start, and that is enough to what I've presented in our presentation.
Okay. Yeah. And then there was actually another question by Stephen here, obviously about the accuracy of your method, right? So how accurate is this method at predicting defects?
Well, so far very good. We have seriously, we have case studies that were monitored by Technical University of Delft and an engineering company and the municipality, and we are very close to what was measured on site. And in terms of detecting damage, we spotted at this 10-meter resolution exactly the formation of cracks on structures.
Okay. So obviously, do you actually have some accuracy figures to give, or is this just anecdotal currently? The evidence.
We have, yes, I mean, we can show data. People can judge by themselves. It's going to be published in June, actually, by the municipality of Zeeland. So we should be able, after the summer, to show exactly the results and what was going on. Yeah.
Brilliant. Thank you. Okay. I've got also one more question. So how do you actually obviously increase the spatial resolution to 10 by 10 meters? you were quite proud, I guess. That's one of the features, right? And can you tell us a little bit more about this? How do you, the INSA data, I guess.
This is exactly the question that all our competitors in INSA are asking. How do you do that? Well, this is a trade secret, but it's based on neighboring analysis and smart sorting of the time series and smart filtering. We use AI. We use AI specifically when we understand what we get from the input and the output. So we use smart algorithms to detect similarities and conformities in a time series that are a sign that they are showing the same behavior. So we can expand our analysis to the neighbors and refine to a specific location. That's why we are able to get to this sort of high resolution.
Brilliant, thank you.
It's a bit complex, but
sure. I understand, and we don't want to give away your secrets. All right. So good. Is there any other further question from the audience? We have maybe 1 or 2 more minutes before we switch to the next talk. It seems it was very clear, Reda. So then let me thank you again for your presentation, and obviously feel free to stay around as well for the rest of the session, and hopefully maybe at the very end there could be maybe another Q&A conversation with the audience and with everyone involved. Okay, so thanks everyone. Brilliant. Okay, so we are like a few minutes ahead of schedule, so I think which is good. So I would like now to invite Yanis and Dan from eOnSite. Perfect, I can see you there. How are you, Yanis?
Hello. Hello. Can you hear me well?
Yes, we can hear you well. Very good. So yes, you can hear. You can also see your screen well. Perfect. So I guess you have a few more minutes anyway, so you can take your time with your presentation, I guess. So
okay.
So obviously I hope that some people who kind of join, maybe they miss the first 2 minutes if they join exactly on your slot, but yeah, let's go with it now. I think just for the case of flow.
Okay, can you hear me, everyone?
Yeah, very good.
Yeah. Okay, so thanks for having us today. And I would like to introduce CHERISH. CHERISH is a cultural heritage INSA. CHERISH is a decision support system for cities to monitor and manage the cultural heritage sites and buildings. But immediately I will let you know more by a live demo, which Yanis will be introducing now.
Yes, thank you, Dan. Hello, everyone. So there's a bit of...
I think, Yanis, your audio is double. I think maybe one of them you need to mute because you're...
this way good?
Yeah, that's fine. Thank you.
Okay. Yeah. So we're going to log in today into CHERISH. Can you still hear me? Sorry, because I have a strange...
It's all good. Yeah.
Okay. Okay. We are going to log in with our demo admin account to the platform. And since CHERISH is a prototype, we have a first screen that invites us to share feedback via email and introduces also the contextual help function, which is available on all pages of CHERISH, and you will see later fully implemented. Next, we land on the onboarding screen. And please allow me to dwell on this screen for a moment because it's really important. The first thing we choose is our language. CHERISH is currently implemented to support all 5 biogroup city languages, as you can see. Of course, I will continue in English. And next, we can select our city. So our admin user has access to all 5 biogroup cities. And you have to know that to start working with CHERISH, we need maps and data. So CHERISH needs a list of cultural heritage assets to work with, but it can be also other types of assets if you're not specifically interested in cultural heritage. As you will see, the platform is actually asset type agnostic. Anyway, so supposing we're working with cultural heritage assets, we need, as I said, a list of those assets, of those buildings. And currently we have an OpenStreetMap based flow, which is available for all cities. This allows you to query a baseline list for any city. Some cities, though, may have their own open data servers or APIs. We can connect to them. We have done so in phase 2, for example, with Ghent's open data for the so-called 7 historic houses dataset that they serve publicly. And finally, the third way is that other cities may have specific data files, like Excel files, which they can upload here if they wish. So this is how in phase 3 pilots, we will collect data and integrate them into CHERISH. And this is how also we plan to address the data heterogeneity across cities. Today, we will continue with the city of Ghent using the OpenStreetMap baseline. So CHERISH queries OpenStreetMap and then suggests a list of assets for us to review and confirm. I will proceed with all suggested assets. We land on the map view, and cultural heritage assets over the city center of Ghent, this square area here, are highlighted as blue polygons. And this is what we call the building footprints. So hovering the mouse over any asset shows its name for the moment. And clicking on it will open its health card, but we'll do that later together. On the top left here, we have a display menu where we can filter by asset category. For example, I can choose only the cathedrals, and there's only one, the famous San Bavo Cathedral. Let's reset the filter. Now look at some more advanced tools. We have the compare button, which opens up a side-by-side split view to compare any 2 base maps. For example, satellite imagery on the left or an OpenStreetMap map layer on the right. This has helped me, for example, to easily identify buildings in cities that I'm not familiar with while working on this project. Next, we can connect external data served by a so-called get capabilities URL. And I have prepared one here. Well, I have just retrieved one here from the internet, coming from Ghent's Open Data portal. When I hit enter, the server of Ghent is queried, and we have a list of available layers that can be integrated into our map. In this case, I will select Straten, which simply means streets in Dutch, and displays the entire street network of Ghent over our map. This can help, for example, city managers to better plan evacuation routes when access is restricted due to structural issues or preservation activities. Let's close this menu now. Now, let me show you how powerful CHERISH is. This button on the top left launches the CHERISH algorithm on space data, as we did explain in our phase 1. Once it completes, our assets have switched from uniform blue to 4 color categories. What do they mean? Let's use the help button to find out. The context explains us that we have 4 categories. The first one, red, means urgent action needed, which means that the building moves in both the horizontal and vertical direction. Yellow means action needed, and it's a building that moves either horizontally or only vertically. Green obviously means no action needed, the ground movement is negligible here. And finally, white, not measured, means that space data coverage is insufficient to draw a conclusion. This applies to very few areas actually on the map. It's the case here, for example, in large squares or over the water, where basically there are not enough reflectors that will reflect the satellite waves to give you information on the movement here. Let's now do a short technical deep dive. In phase 1, we explained how CHERISH groups satellite data measurement points into cells of different sizes on the maps. These cells are shown here. There are two types of cells. The pink ones show abnormal values of displacement. You get the mean displacement velocity either in vertical or horizontal direction when you hover upon them. And the white cells show measured areas without significant ground movement detected. And as you see, the area I was talking about before, this open square, let's say, or a not built surface, and the river, and also this square here, are not covered actually. So basically, the current coverage in this example, this square area here, covers Ghent historical city center, and it's the area we have worked on. In phase 3 pilots, this can be adapted when you confirm your own municipality boundaries more precisely.
Okay, thank you, Yanis. So now we have the city-wide prioritization of assets by urgency and actions and things to do. So we see that the Cathedral of Saint Bavo is red. So what do we do now? Show us.
Yes, indeed. So we have to do something, but no operation has yet been created as the tooltip shows. So clicking on Saint Bavo, we land on the so-called asset health card, which is the central integration point between satellite monitoring and day-to-day asset management. We have the monitoring tab here on the left, which contains basic building characteristics. And on the right, it shows the CHERISH index, which is red, and CHERISH recommends urgent action for Saint Bavo. There is also an optional city assessment override. This edit button opens this score matrix that combines the CHERISH index with the city assessment. And this determines the final status of the building. The horizontal axis corresponds to the CHERISH index and the vertical one to the city assessment. This means that local knowledge can say, for example, that this building was recently inspected. Therefore, the city may override our satellite recommendation by choosing no action needed, and everything goes green. We would really love to work further on this feature during the pilots. Let's assume now that we don't have any additional insights, and we will follow CHERISH recommendation. Here we have a minimap, which allows us to dig in a further level deeper into the space data analysis if we wish to ask for more expertise from the system. So in this minimap, we see again the average velocities of the cells, and clicking on the cells that we are interested in, we visualize their time series along with their average velocity that has been calculated, and can link these graphs to the map. We can also do this on the vertical movement and switch back and fro to do our analysis in the required level of detail. We have also developed a cool feature that makes us ready for the digital twin era and smart cities. I will now switch to Helsinki, because Helsinki provides already open 3D data on 3D building models. And this is the health card of the Uspensky Orthodox Cathedral in Helsinki. CHERISH has detected abnormal ground displacement and recommends action at yellow level. So this time, below the minimap, we have an additional insert, sorry for that, that shows the church and terrain in 3D. we see some visualization artifacts here from the model. Now, when we switch this tab to, sorry, I got kicked out. Just let me log in again. So this is Helsinki, by the way, and our nice cathedral. So I'm back as before on the 3D model. So I was saying that when we switch the model to the so-called surface model, the view changes and the wall surfaces turn gray. The roof surfaces are simply colored red. This does not mean they have a problem. They're just colored like a brick color, let's say. And we have some additional colors. For example, here, this part of the wall or this one here, where we could calculate an average velocity for that wall or roof surface because the data was available on that area. So these surfaces are not necessarily problematic. They just mean that enough satellite measurement points are available to do the calculation. And this model, more generally, can be used by the city as a guide for where to focus on-site field inspection effort first. For example, this part of the building. And the 3D feature makes CHERISH future-proof because whether cities will develop digital twins is not the question. When is the question. So switching back to Ghent and Senbevo, I wanted to show you this section at the bottom, which is currently populated with mock data. If provided by the city, this reflects real visitor figures and helps prioritize response because highly visited sites with anomalies require faster action than less frequented ones. We can also export this health card as a PDF ready for example, stakeholder presentations, budget requests, or technical reviews. I get a PDF downloaded on my PC, and you see that it contains all the information of the health card. It also will include a 3D model if available and the rest of the page. So this export could be used as technical evidence by a structural engineer or conservator who needs to justify an inspection in their next budget cycle. Now that we know that Senbevo needs some care, what do? Clicking on the building status opens up a dialog box to create an operation. Let's plan an inspection, obviously, for next month, which, let's say, will cost us €1,000. It's the first inspection. And we can upload, for example, a quotation that we have already received. So this creates a list on the Operations tab of the health card of Senbevo, which lists all past and planned maintenance operations for this building only. The information is summarized in this table. Operations containing attachments are marked with a paperclip, and filters allow to search for operations. Clicking on a row allows to edit or delete the operation, and we can also click edit the status, overdue, to do, in progress, or done here. And by the way, the overdue, for example, will be triggered automatically if the start date has been exceeded without having switched the status manually. You may have noticed this pink dot on the left. This flags operations driven by CHERISH's recommendation. And this flag is set automatically when an operation is created from the button of the health card, like I just did. This lets us measure how many satellite alerts have actually been translated into scheduled field operations. And it's the core metric of CHERISH's value proposition, which is not just detecting the formation, but closing the loop to documented response. The inventory tab is obviously still under development. It's a mock feature that we have imagined, which allows us to track movable items inside a building, artworks, furniture, objects of cultural or insurance value. Currently, it's populated with mock data, and in phase 3, this may reflect the city's actual inventory for this building. I will now close this help card. So, by the way, now when we hover over Saint Bavo, we see that an operation has been created in one glimpse. So to summarize, we have moved from a city-level view down to an asset-centric view, and then over to operations scheduling. And to further support a manager on the daily operations management, they can find here on the left the full list of assets they manage. And here you see assets in Ghent and in the other 5 cities of SPACE4Cities, because I am the admin user, if you remember, and I can see all the assets across the 5 cities. So you may ask, for example, how can I use this list outside? We have an export button again, but this time we don't get a PDF, but a CSV, or basically an Excel file, where we have extracted this entire list. I can work on it or reprocess it into our own city tools if we wish to.
Okay, excellent, Yanis, thank you. So this is the list of assets, the global overview of the assets. And how can I now know what to do next month, for instance?
Yeah, thanks for the question. So that's why we have implemented the operations list, the global operations list, containing all operations created across all assets. For the purpose of this demo, you see that we have already created several entries to show you the last feature, namely the dashboard, which provides monitoring and operational overview at a glance for Ghent in this case. And it's organized in 3 panels: your assets, which is a total inventory count broken down by category. And we have also included a mock count of UNESCO designated assets, because UNESCO sites typically trigger specific reporting obligations, but also open potential funding opportunities for repairs. Under the monitoring section, we find the CHERISH alert distribution and coverage. The number here, 42, summarizes the buildings requiring attention, so the red plus the yellow ones. And finally, in the management, we have the operations workflow status and budget analytics. The colors here do not correspond to those. They are linked to the status of the operation and not the alert status of the asset. By the way, we are proud to share that for Ghent, first of all, that this data is directly from CHERISH's processing of space data, and to note also the high coverage in this case for Ghent of 97% of the assets measured. The remaining 3% here correspond actually to statues or small monuments, which are too small to be captured by the satellite radar. And this dashboard is exactly what we need, for example, for quarterly review. In particular, the budget chart summarizes maintenance spending, giving the planning team a different but crucial perspective. And once again, this dashboard is exportable, this time again in the form of a PDF, which can be shared across further instances in the city's daily life. So Dan, I give the floor back to you.
Yes, thank you, Yanis. So let me now talk about a bit about interoperability between the existing municipal systems and CHERISH. So we have a 2-level interoperability. It's ensured by both the capacity to import data into CHERISH solution and export from CHERISH to your municipal system. So you can import into CHERISH the city-specific data files if and when you have them. I must stress that if a city does not have specific data files for geodata files for its municipality boundaries, it's not a problem. We can use the default OpenStreetMap data. And when the city has, then we can import that and to offer a different level of service and specificities. And also we can import into CHERISH the maps by geodata, URL, or maps like we showed. We can also export with Excel and CSV files or PDF files as we showed. Next slide. And we also have this very cool feature which allows to interoperate with the, let's say, professional advanced GIS, Geographic Information System expert. And we can totally export the analysis made by CHERISH on the cells with issues, as we showed, with abnormal movements. We can export that directly to Copernicus website and to the QGIS expert system that many cities use. But again, if you don't have one, it's not a problem. So this is about interoperability. Now, what we want to express is that what you saw is working. CHERISH is currently operational, and it's a real-world solution. It works. And it answers many different questions from different stakeholders, like, for instance, show me all the assets at risk in the historical center. Bim, you have the map and you have the buildings highlighted. Which sites should we prioritize for the next inspections? Well, you should have the little color code explaining you which is red, urgent, which is needed next, and which is not for the moment. So we have this prioritization possibility. And also something which is very important that we miss is the issue of budget, because budgets are constraints. So operators need to know where they stand in terms of budget. So they need to be able to follow that some budget go for reconstruction, some go for plane inspections, and some go for the full maintenance operations. So this is also a tracking possibility that is very useful for the cities. And this is it. Basically, you saw that we can use CHERISH and deploy it very easily in 3 clicks. And we encourage you to deploy CHERISH now in your city. And we stand ready to help you do that. Thank you very much.
Brilliant. Thanks you both, Yanis and Dan, for an excellent demo and also presentation.
Thank you, Alex, for organizing this.
No, that's fine. No, a pleasure. Yeah, we've got actually a question by Peter Jan. I can read it out as well for you guys. It's a bit of a long question, but okay, let's do it. Have you thought about distributed ownership regarding operations? How this reflects in your interface? It probably is the case that the cities manage a part of the cultural heritage buildings, but others, like the Queen St. Baths or Helsinki Cathedral, are managed by religious organizations. So,
yes.
So such report could be at least a signal from the city towards the owners of the assets on next steps and ask follow-ups in regards to operations.
Yeah, so we totally have thought of that, because it's what the person Mr. Powell's expressed is exactly the case. Specifically in Ghent, there are different institutions, so I mean to call them, in charge of different buildings. There's the regional FLAMS thing, and so there are different entities, and that's exactly what this unified integrated platform intends to solve and to streamline, is the relationship between such parties. And we didn't show that, but we have prepared roles and attributions, so that, because Yanis is the Uber power user, so he can switch from Helsinki to Ghent to whatever, and switch from Greek to Finnish. But the truth is that normally it's segmented, so that the firefighters don't have access, for instance, to the budget, because the firefighters need to know the map of the road and where is the church and where are the entries and exit and stuff like that, and see that on the map quickly. They don't care if the budget is 10,000 for next year's maintenance. So everything that you saw is a feature which is by construct a granular module, and we open the authorizations, the roles of the users, the stakeholders, differently, so that you may see the budget, don't see the budget, you may have access to the full calculation, or you don't. So it really is something which is embedded, but we can't show it now because Yanis is a super power user. So and again,
Okay.
if you're Finnish, you don't see the Greek.
Got this, yeah. But what does it mean? Does it mean that, for instance, the church organization will have to be also a tenant on your platform, or will it just mean that the city can invite them as a user
exactly
with restricted rights?
The city will invite them. The city will invite them, saying, "Hey, Mr. XYZ from the diocesan organization, we opened you a user account where you could have access to the church and what's inside. Because if you want insurability, for instance, you better have a list. I don't know if you have a list, but that's the option. We have a 3D model of the church. You just complete it with the asset list, and then you can track them. So effectively, the idea is to onboard each of the various stakeholders easily through the city in a manner which is not seen as a constraint. It's because it provides, it contributes, gives benefit to all the stakeholders, so they would join. Okay, good. Perfect. But obviously, I guess in this case, the city would be the one who would pay for the platform, right? But then obviously engage with other organizations as well and allow them to participate or take advantage of their insights. Yeah. Okay.
I mean, we can very well create an account for the church if they really have many assets to deal, and it's like a pseudo city in this case. So. We could also do a platform only for the diocese, so for the church organization, so that they manage. I don't know. They have 20 churches in the city. They manage only their own 20 churches and not the others. We could also think of that.
Cool. Thank you. So, are there any sort of other questions from the audience here? We've got a few more minutes. Everyone's shy, or it was very clear. I mean, I have maybe one more question, just if you allow. So it was obviously I could see that in your tool, you are also sort of like listing which buildings require action. But do you actually also recommend specific actions other than an inspection, or will everything depend on the inspection from your tool?
It would depend on the inspection.
Yeah. Okay.
So what the case is, we use space data ground movement. So what we know and show is that there is an anomaly in the ground movement. So our job is to tell you guys there's an issue with the ground movement, and that's what the CHERISH index expresses and alerts. It says, guys, it's red. There is something abnormal on the movements. Once we say that, the city users, the city operators will tell us, no, we know, we've been there yesterday, it's okay. So that's why the city assessment is very important, because the city guys know, they know two things. They've been there yesterday and it's okay, fine. And also they know that they will go there tomorrow, so it's okay. For two opposite reasons. But sure, we are planning to do big things, so it's okay. It can stand another week. So that's exactly why we need the participation of the city users and people knowing the ground truth, because they are the ones saying, okay, yes, that's interesting that you saw something with the satellite ground movements, because we follow that very, very carefully, and we are aware. So our alerts, we just trigger the confirm to the persons using it that it's okay and that they're following the right course.
Thank you, Dan. Perfect, thank you. So I guess we will now switch to the next presenter. So as time is sort of ticking. So thanks again for your talk.
Thank you.
Thank you very much.
And now we will also not only switch presenter, but also topic. So before we had obviously had a series of talks focused more around structural health. And Denise will now look more at a different topic, right? Around water leak detection in the city. And so, yeah, I'll hand over to you. Feel free to take the screen, Denise.
Perfect. So good morning, everyone. I'm Denise of Neptune, and we are now working in the Urban Lens project thanks to SPACE4Cities. I'm going to share my screen with my presentation. Okay, so good morning, everyone, and thank you for being here. It's a pleasure for us to working with SPACE4Cities on our project. Today we are presenting our project and the status of our solution that turns European space data into a concrete operational tool for city infrastructure management. I'll guide you through our solution, where we stand today, and the results that we obtained in these two phases. So let me start with the problem we are addressing. Across Europe, cities lose between 20 and 40% of treated water before it even reaches home or businesses. These leaks happen underground, often for months, and nobody notices them until the road collapses or someone complains about low pressure. The methods used today are mostly reactive. We have acoustic sensors and manual inspections. They work locally, but they're slow and can only check a few streets per day. Meanwhile, water utilities have no way to monitor their entire network in a continuous and cost-effective way. So that's why we asked ourselves a simple question. So could we use satellite to also help cities manage their underground water networks? That questions led to the creation of Urban Lens. Urban Lens is a fusion between space technologies and urban operation. We combine two major European space assets. First, we have Copernicus Sentinel-1, from which we use radar interferometry to detect very small ground deformations, sometimes just a few millimeters. This can indicate subtle subsidence or uplift caused by persistent leaks underground. Then we have the GNSS-R that measures changes in soil moisture by analyzing the reflection of satellite signals from the ground. Alone, these two datasets have some limitations, but when we combine them, something powerful happens. In fact, deformation and soil moisture together reveal where leaks are most likely occurring, and with much higher confidence. Urban Lens then processes this information automatically and fuses it into a single geospatial model, generating an anomaly confidence score for every pipe segment. So at the beginning, we defined a very clear plan. The objective for us was to move from a concept to a system that is ready for real-world deployment. We focused on 5 key areas. So the first one was finalizing and validating the GNSS-based sensing system. Then we integrated the fusion between satellite and ground data to deliver also the usable platform, to validate the solution through multiple testing and collecting feedback from users. Our target was to reach a TRL from 6 to 7 prototype at the end of the phase 2. The benefits for cities were tangible and measurable. In fact, we have up to 350 kilometers of network monitored per week. A reduced inspection time, so from detection to verification in less than 5 days. Unmeasurable reductions in water losses and CO2 emissions. a faster response time for maintenance rules, and a scalable and affordable model that any European cities can adapt. So after defining the plan, our focus was on execution. The objective was not just to develop components, but to make the system work as a whole. Starting from the sensing layer, the GNSS hardware has been stabilized and validated in real urban environments. At the same time, we completed the integration between satellite-based analysis and ground measurements, achieving a fully operational data fusion layer. On the platform side, we delivered a working viewer and API suite.
Hello, Denise. I think we lost you for a moment.
Sorry?
Okay. Yeah, now
Yeah.
it's fine. Perfect. Yeah, I think you
Okay,
sound
perfect. Yes.
Perfect.
So on the platform side, we delivered a working viewer and API suite, enabling both human interaction and system integration. And then, most importantly, we validated the solution through multiple field campaigns and continuously refined it based on real feedback from the field. The result now is not just a prototype, but a system that is ready, stable, consistent, and ready for piloting. So one of our main objectives was not just to develop the system, but to make it work reliably in real conditions. And this meant addressing also several challenges. The first one was due to signal quality. In fact, on urban environments, GNSS signals are affected by multipath and noise. To address this, we introduced the advanced filtering techniques and multi-satellite analysis, improving the stability of the measurements. Another challenge was related to the installation. In fact, since the system is mounted on vehicles, the configuration needs to be robust and repeatable. For this reason, we made some improvements to the instrument installation on the vehicle. In particular, we adjusted the mounting configuration and increased the height of the antenna, moving it about 30 centimeters farther away from the vehicle. Doing this, we increased the effective Fresnel zone, which is the ground area contributing to the reflecting GNSS signals used in the reflectometry analysis. We also faced a relatively high number of false positives during early tests. This was addressed through algorithm improvements, including adaptive thresholds and persistence logic across multiple signals. Finally, we needed to ensure that the system works in different types of urban environments, and this is why we tested it across multiple cities, progressively improving its robustness. The result of this work is a system that is now stable, reliable, and ready for real-world validation. So we designed a progressive validation approach in real environments across multiple Italian cities, each with a specific role. We inspected 355 kilometers with a total of 43 leaks confirmed. We started from a city in the north of Italy, that is Bologna, where we performed the initial validation and calibration. This allowed us to confirm the feasibility of the approach, but also to identify limitations, especially in terms of false positives. Then we moved to Belluno, where we tested the system under different environmental conditions, especially in the mountain, improving its robustness. The next step was Rovigo, that is a city near of us, where we focused on more operational scenarios with less controlled conditions. After that, we returned to Bologna to directly compare results before and after improvements. Finally, we conducted the last validation campaign in Pisa, confirming the readiness of the system in an additional urban context. Across all these campaigns, we analyzed several hundred of kilometers, as I said earlier. And what is important here is not just the individual test, but the progression of the system improved continuously. And also reached a stable level of performance by the end of the first and second phase of SPACE4Cities. So now, instead of explain further, we would like to show you how the system behaved in real conditions across different validations campaigns. So I have a video that I'm going to show you.
Yeah, the video was working, but I guess not the sound. Yeah. Was there some sound expected or not, Denise?
Yeah, there is a little sound. I don't know if you hear it.
No, we don't hear the sound. No. Maybe
Okay.
maybe you can just comment loud what's happening. So
Yeah. Okay. So the quick question is, how does this translate into real usage? Here you see the installation of the instrument on the vehicle. The system is designed to be simple and flexible, allowing data collection directly while driving through the city. The instrument is mounted on the vehicle and continuously collects GNSS signals during the survey. An important aspect is that our support of the instrument is made of wood, a material commonly used also in ESA tests for electromagnetic system, because it doesn't interfere with the signal. So this helps us to ensure that the measurements are as clean and reliable as possible. So now you see that the vehicle goes from our laboratory and started collecting data. The vehicle moves just simply through the roads, analyzing the water networks, and the system collects data over large portions of the roads in a very efficient way. So this allowed us to monitor tens of kilometers in a short time without the need for fixed installation or complex setup, and it can be installed on any vehicle. So then after the data collection, the information is processed and uploaded into our platform, where it is combined with satellite data to generate anomaly maps and confidence indicators. The system then analyzes the GNSS signals and identifies variation in soil moisture, generating georeferenced points that highlight potential anomalies in the ground. These points represent areas where abnormal moisture conditions are detected, which may be associated with underground water leaks. The processed data is then uploaded into our platform, where it becomes available for visualization. Through our dashboard, operators can clearly see the anomaly points, analyze their confidence level, and prioritize inspection activities then. An important aspect of our approach is the validation of the results. In fact, thanks to our collaboration with water utilities in Italy, we have access to network data and operational support. So this allowed field operators to perform targeted inspections and confirm whether the detected anomalies correspond to actual water leaks. This validation process ensures that the results are reliable and gives us strong confidence in the accuracy of the system. So now you're seeing what we are doing after the data collection of the vehicles, just I said. Okay. So this is our dashboard, the Urban Lens platform, and all these results then are then accessible through our platform. Here, users can visualize anomalies, check confidence levels, and prioritize inspections. Here we are going to see our dashboard and how it works. So we are just enter in the dashboard. We have our project. And here you can see each test we have done during this month in Italy. So I'm going to show you just an example of a validation test that we have done. Here you see the interferometric analysis we made. This is the first test we made in Bologna, in the north of Italy. The blue line now represents the pipeline, so the water network. Then we have in orange the geotrack of the instrument. Meanwhile, now in white, we have the areas detected by the instrument in which there is some soil moisture. And then finally, in red, we have the water leaks confirmed by our operators. In fact, thanks to our collaborations and thanks to our operators that work in the field and confirm leakages, using traditional methods, we just walking through the roads and hearing noise through a geophone, we have the confirm of the water leaks detected by our instrument. Now there is a second example of a test made in Belluno. Here what you see is the difference of the territory analyzed. It was our first time in a mountain. So for us, it was just a bit challenging, but the results was very good because all detected areas that are the white ones then represented leaks. So the second test was very good for us, and also even if was very challenging. So this is our dashboard. Just two example, but every test that we are doing is uploaded into our dashboard, and then each user can visualize it. It's in English, so then operators can prioritize inspections and activities of the cities. This is a recap of each test we have done during this month. Here you can notice the difference of the territory analyzed. This was for a preparation for an eventual pilot of different cities and to be prepared of the difference of each cities that we have to pilot. Here you have the interferometric analysis made for each territory of the test. And here, so the noise, I don't know if you hear it, I think no, but here is an example of a report made by our operators. So when we have to check if the instrument have detected a real leaks, we go with our operators that just simply walk through the roads and confirm it with a hearing. So hearing the noise of the leaks of the water. We have also the position, the GPS position of the water leaks. We have also the the urgency of repair of the water leaks based by the water leaks noise and liters by second. And also some pictures to effective see of the leaks. So before concluding, I would like to briefly outline how we plan to move forward in phase 3. We plan to implement the pilot activities in one buyers group cities, testing the system in real operational conditions, and evaluating its usefulness for municipal water management. The pilot will be carried out in close collaboration with local water utilities and city technical teams. During each pilot, we expect to survey around 100 kilometers of network, collecting data that will be processed and combined with satellites information to generate anomaly maps and confidence indicators. These results then are accessible through the platform, enabling city teams to prioritize inspections and to support the maintenance decisions. To make this possible, collaboration with cities will be essential, especially in terms of access to network data and coordination of field activities. Overall, phase 3 will allow us to validate the solution not only technically, but also in real operational workflows, confirming its readiness for large-scale adoption. So to conclude, thanks to SPACE4Cities, we have transformed Urban Lens into a working and validated system. We have demonstrated that the solution works in real urban environments, that can be deployed and operated in practice, and provides useful information for end users. So we are now ready, we hope, to move to phase 3, where the focus will be no longer term deployment, but integration with city workflows and large-scale validation. Our objective is to move from a prototype to a solution that can be used on a daily basis by each cities, not only in Italy, but also in Europe and maybe also worldwide. So thank you for our attention.
Excellent. Thank you, Denise. Very clear presentation. Much appreciated. Good. Let's obviously, as always, we have now an opportunity to ask questions, obviously. So I'll open the floor now to everyone who might have a question regarding your solution. So feel free, don't be shy, just raise your hand and we'll get you engaged. Or alternatively, just paste a question in the window. Okay. So while we're waiting for my questions to come, I have a few myself. So
Yes.
it's okay. So obviously, so one is really regarding you know, the survey that you do now with your instrument, right? So you're driving obviously down the roads, but I guess you need to know actually where the water network is, right? To better plan the routes of the vehicles. No, because some roads might, some roads don't, right? Have water. Yeah. So is there like so do you have like before you actually do the survey, do you have some sort of planning, route planning or something like this, where you kind of obviously look first at the water network map and then say this is the roads we need to drive, or how does it work?
Yeah, that's a good question. In fact, actually, we have to have the water network data before to do our test, and then we plan our test. Knowing this information, we don't need any critical city data, but the water network layout, so the pipeline geometry. Or eventually some information about historical leaks, if were present, are very useful for us. We cannot do it without the pipeline geometry because we have to do it with it. So we have to coordinate with city or technicals, water technicals, technicians in cities before doing the test, and then we plan our test. Then also in Italy we have our vehicle that simply roads through the roads. But the instrument doesn't need any fixed or complex setup, so we just can put it on any vehicles. So in each cities, we just need a vehicle, a car, and just do it, knowing where is the water network.
Brilliant. Thank you. Thank you. Actually, I think my question triggered more, which is good. So there's one by Irina, which I hope to try to understand. Is it possible to calculate the real value of money thanks to such road monitoring? I guess maybe what's the sort of like savings that your solution brings to the table? Or actually, she clarifies now. So she wants to maybe understand whether you can create road repair estimates. So like, obviously once you detect a leak, can you estimate how much it will cost, or is this subject to the surveyor? So does your tool do that, or is it someone else who needs to assess that?
Yeah, actually, we just identify water leaks,
Okay.
and then others repairs. So our works is just to save water, to help cities, to help also to save also the safety of the citizens, of the homes.
So,
Just also, for example, to save money in homes or businesses before the leaks happens.
perfect.
Yeah.
Perfect. Understood. And then there's a second question by Peter Jan. It says the water network might be under the pavement of the sidewalk rather than the street. Can this be detected as well with the setup tested in Italy? So obviously, maybe you might not drive directly over the pavement, but the water pipes could be there. So what do you say here?
Yeah, we're just testing with a robot that is a dog robot. We tested it in Belluno in the mountain 2 weeks ago, and it went very well. So we can go not only in roads, but also, for example, in mountains areas or in areas in which the vehicles can't go. For example, due to traffic limited zones. Or some areas more challenging, like, for example, mountains.
Sure, cool. So basically, maybe to answer the question, not directly, but if you have like a sort of robot or something like this that can go on a sidewalk, or obviously you can mount your solution on other sort of vehicles, right?
Yes.
Like this. Perfect. Okay. And bikes was another suggestion. Very good, Peter. Yeah, potentially. I've got one more thing before moving on, but I mean, this is like maybe a quick one. One is like about the deployment environment. Yeah. So what happens? So how deep does the pipe work?
Yeah.
Can it maximally be for you to detect it reliably? So one question. The second one is, what if it rains, right? Obviously, the moisture might be biased. How many hours, days it should be dry before you do this inspection?
So also when we done this test during these months, we had some weather challenging moments. So when because in Italy it rained a lot this winter, but for example when rain we wait just 3 or 4 days to the roads that can. And then the vehicle can go. And pipes are, for example, about 1 or 2 meters, so we can see it
Okay. Thank you so much. Brilliant. Sorry, there was one more last question quickly.
Yeah.
So basically, if a water leak happened due to a flood, not to a water network, I'm not quite sure if I fully understand, but I guess whether there was a flooding causing, I guess, the moisture rather than a water leak in a pipe, I think. Yeah.
Yeah, I don't know because we detected.
I guess it's maybe similar to the rain, right? Scenario.
Yeah.
Once it dries up, then you can detect it, right? So,
Yes.
yeah, perfect. Okay, thanks so much, Denise.
Thank you for the
And
opportunity.
obviously, please stay on for maybe the final sort of
Yes.
panel conversation later. But I will now want to invite our last presenter, Mathieu. I can see you're going live from Ever Impact. So, Mathieu, thanks for joining, and the floor is yours.
Thanks. Hi, everyone. Mathieu from Ever Impact here. And I will share my screen. And we come under the project DYNAMO-SM. Project. So today we'll have two parts in the presentation. First, quickly on the company, what we do and where we're going, to show you a little bit the background of the project, of the DYNAMO-SM, and then Lorenzo, my colleague, will show you a bit of demo of the data we have on the project. So Ever Impact, we specialize on greenhouse gas emissions tracking, and we are in the process of building a greenhouse gas emissions tracking system of satellites and sensors by fusing the data, and especially for cities, which we have done now for many years. Briefly about us, we are a climate tech startup with basically the founders who were CEOs in the United Nations. We have scaled similar ventures before, including a UN satellite agency called UNOSAT. And about 10 years ago, we decided to focus on climate and especially carbon emissions tracking. We now have a team of 15 people, headquarters in Paris. We have a daughter company in Tokyo and an office in Copenhagen. So that's a bit about us. We have the particularity also to have the EU Commission as an investor and shareholder, together with other venture capital firms such as Mitsubishi and other international organizations like the Asian Development Bank, basically allowing us to work very closly with cities and the EU. And I think it's a bit of a particular status for a startup, but we are very happy about this and to be trusted by the EU. So when we talk about carbon emissions and cities, what we have seen now in the past many years is that they rely on estimated data and statistics. And let's not forget that cities have represent about 70% of emissions globally. So cities play a big role in the solution to reduce emissions and decarbonization. We see also that statistics are currently estimated fuel emissions, traffic estimates, and so on, is leading to 150% reporting errors in some cases, worst cases, and we also see there's often 30 to 50% errors. And we are basically trying to change this. And also we see that because of not having good data, there's 30% of missed reductions. And that means in terms of economical and valuatory money, 0.3 to 10 million euros missed savings per city annually because of having bad data. So we are on a mission to change this, and our solution is to bring CO2 monitoring every hour, every 10 meters, anywhere in the world. And what you can see here on the screen are plumes of emissions. So emissions are not static, they are not statistics. As you can see, they are moving, they are pushed by the wind. You can track them and go back to the origin to see who's the polluter and what is the source of the pollution and the emission. We have high precision with sensors and satellite. it's independent data. It's not produced by the polluters themselves, so you can verify this independently. And we have developed, we have patented our technology on 4 different markets, and we can identify who's the polluter. So we are really trying to depart from statistics and bring real accuracy to cities. To do this, we fuse data from satellites, sensors, and AI. We today have about 150 sensors being deployed in Europe, in cities such as in Dijon, but we also have them in other cities like London, Birmingham. We're deploying in Lausanne, Bern, Zurich, and so on. We also have them in ports, like you can see here, and on ships. We also rely on satellite data, and today we have already 9 cities using the system. We have the SPACE4Cities program, but we also have the system in cities like Dijon. I mentioned London, Birmingham, etc. But we're also starting to deploy very soon in other parts of Belgium and also in France with the Paris region. The system allows automatic data capture and save money on this, because currently cities take about 2 years to gather data from consultants and put it into Excel spreadsheet and statistics. We automate this data capture, so cities can focus on analyzing data and in finding insights rather than compiling it. And it gets data every 10 minutes instead of every 2 years. And this informs decisions and policy making, finds more reductions and hotspots, and leads to access to green finance and savings. So these are the benefits of the tool. And we are making great progress as we work through the phase 1 and phase 2. In parallel, we recently secured an investment of 7 million euros from the EU Commission and EIT Urban Mobility and some venture capital firms to launch our first satellite and move from public satellite data to our own constellation. And the launch is scheduled for Q3 next year. And the vision is to have over time 10 small satellites and 5,000 sensors deployed globally, and bring a global tracking system of greenhouse gas emissions and air quality as well. And as part of this investment, we also have the city of Paris, the region Île-de-France, which represent 1,266 communes, to deploy our sensors and calibrate this with our satellite. And we're also starting to expand also in Mechelen in Belgium, and in touch with the Net Zero cities to deploy more satellites and create a ground network in cities, and bring basically a global network to more cities in the world from a European base. We are always seeking for cities to be equipped with our sensors and help expand the network. And we're really trying to move from 10 cities to the next milestone is 20 cities within 12 months, and then increase to thousands of cities in the next 5 years. And we're always seeking for the early adopters, so feel free to reach out to us. And I will now pass the floor on to Lorenzo to show a bit of data and the demo of the system.
Hello everyone, I'm Lorenzo from Impact. I hope you hear me and see me well.
Yes, yes. The small hole effect, but yeah, we can hear you well. Yeah.
Okay, great. So you should see my screen now. I'm very happy to show you this demo live. The objective, I know we are the last demo of the day, of the second day actually. So thank you for bearing with me. I hope you find this interesting, and you will see how we are actually stepping up the understanding of emissions over territories like cities and ports, as Matt was explaining. So we start from the ground zero, let's say, or the point where we see our customer are right now, which is a complex framework where you have to link together a lot of different data. You probably need a couple of experts to understand the data for reporting. And in the end, the reporting is made for 1 or 2 years in the past with high granularity. So it's very difficult to have a link between the data that you take so much effort to crunch and prepare, and something that actually is actionable on the territory to improve the life of your citizens, to save money, and to have an informed decision-making when it comes to emissions management. So the first thing that we see, trying to simplify all the story for the users, is the onboarding. Here I am simulating a first login as a user. I can tell you the spoiler, this is not my first login, but indeed, as a first login, we have an onboarding system that I will pass through. So we have a welcome as a first thing, and then we are going to briefly explain what are the different elements of the dashboard. So what we can play with. We see that there is a copilot, which is interesting, especially in use case when we see one, but we try to extract insights from the data that we not necessarily understand 100%. We don't need to be heavy technical guys to navigate this platform. We see that we have a filter section where we can play with time, with sectors and places. We see that we have a graph visualization. Again, trying to keep it as simple as possible. So we have a time distribution of emissions. We have sectoral distribution of emissions. We have a map, which is the centerpiece of this specific module of the dashboard, which allows us to explore and see the visualization on a map, which is something that today is quite impossible, at least at this granularity level. And we have a map control section. So here we can easily control the elements on the map, such as the graph that I was showing and the couple ones that we will play with in a second. It's not, and it doesn't finish here because we have a dashboard and the insight section. We will see an example in a second, but I just want to raise that this is a very important and very successful module in our dashboard when we discuss with cities like you, because it's where you are able to ensure that you're tracking what matters to you. We will see in a second how a dashboard can be set up. And this is a customizable aspect of the dashboard. So it's something that we normally, together with our users, we develop to ensure that the KPIs, the tracking are relevant to specific use case per each city or specific stakeholders inside a different city. There might be a decision maker, a politician that wants to see something and track something, or different neighborhoods inside the city that want to track specific areas inside the city. And I can go on and on with possible use cases. Now we are ready to explore, so I will start the exploration and show you that here we are looking at the city of Dijon. We see a map, we see some colors on the map, and we can start to click some buttons to understand a bit more what we're looking at. I'm sure you already guess what we're looking at. So this is emissions of CO2. I highlight a lot the word emissions, not concentration. We are used to see concentrations of CO2. The big innovation here is that emissions are allocated to specific source point emitters. So we are not just looking at the concentration of CO2 or different pollutants on a city. We are looking at who emitted a specific amount of CO2 in tons, which is the same value that in the end you will be asked to report when you do any emission reporting. So we translate, this is just an example actually of how we translate raw data into usable data. Then if you want to understand a bit better the color, we can activate the legend, for example. We see that red goes to higher emission level and yellow, towards the yellow, we go to lower emission levels. And then we can see that with the over, I can start to understand the different hexagons, the different emission level on the hexagons. I can zoom in and see in more detail what is the level of the city, of emissions of the city. And another practical thing that we will use shortly, I can play with the opacity as well. Maybe the hotspot weren't that clear 1 second ago, but now appear very clear on the map. So let's see a couple of use cases and why I say that we are stepping up with respect to current understanding. I think this is already a step up. So we are looking at emissions over a territory with very high granularity with respect to what's available today, but that's not it. I mentioned that we have different sectors, so I'm opening the filter part and I can play a little bit with the sectors here. You will see how the emissions distribution on a map changes accordingly while I select a specific sector. A very striking example, in my opinion, in Dijon is when I select other sources of transport that is not road transport. So here there is airports, there is railway, for example. And when I zoom in, I can see how precisely I can go on the train station here, and I see the emission level on the airport, a clear hotspot. So this is just to show you how geographically distributing emissions already will let you know, okay, that is where my emissions are coming, that is where I should look more deeply. This is in terms of geographic distribution of the data, but we mentioned that we have also time distribution of the data. So by opening the graph here, I can start to see that I can select different months of emissions. We are looking at 3 months in 2025 for this demo. And I can go actually much in detail, so I can decide to enter in a specific month and start to look at the trends around within that month. And I can even enter more in detail and be interested on a specific day and start to see what is the level of emissions moving every hour on that specific day. This is another clear example of how we're stepping up. So we talked about 1 hour in the past. Here we are looking at hourly updated data that are accessible to have a much better understanding of what is happening actually in the city. Now, let's look, to not bore you, at a couple of use cases that we can spot here. Just looking at the time, but we are good. So when I want to have one of the use cases that I wanted to show you is, for example, residential housing. When I click on residential housing, which might be an interesting point, well, we see that there is a clear hotspot area, which is the center of the city, not a big surprise. Again, I can play here to see better what is the hotspot area. And let's say that I am interested in this specific hexagon. Well, this is higher, so let's go here. I can select a specific hexagon, and this is something else that I am adding on the table because I am interested in that specific area for any reason. When I do this, everything else updates, and I can see the distribution of emissions on this specific hexagon. So I can see that this specific hexagon has a bunch of houses. It captures also a big road up here. There are other roads, quite important roads here. And we see this reflected in the level of emissions and the split of emissions. So we see that mostly we are looking at road transport and residential housing, almost in the totality. And again, I might be interested in monitoring this area. So one thing that I wanted to show you is now that I have this selection, and let's say I am interested in monitoring June for any reason, then I can save this selection and call it center. You have to give me 1 second for my battery saving feature of the keyboard kicks in always in the wrong moment. But this can be center emissions area 1. Then I can save this element and I clear my filter and I go to look at something else. And when I want to go back in this module or any other module, I can access my filters here and go back to the level that the selection that we had previously, exactly in the same time and with the same filters that were applied. A second use case that I wanted to show you is kind of the elephant in the room, I would say, is about the road transport, which is a very interesting use case for our users. And here there is a very interesting use case on the city of Dijon. Here as well, there is quite a clear winner in terms of hotspot when we look at the map from far away. And this is the incriminated hexagon. So we can look more deeply here to see what we can find. And we clearly see that there is this big crossroad which I can select, and I can see that 99.9% of the emissions here are allocated to road transport, which is quite expected. The interesting part here is when you start to look at this data with the knowledge that you in the city have. So in the discussion of Dijon, this was a very striking insight actually, because they didn't expect to find this high level of emissions that, by the way, are accounted to the city of Dijon, but are actually caused from transfer vehicle moving, not necessarily inside or outside the city of Dijon, but passing from north to south in this road. And this is actually accounted to the city of Dijon when we look at emission levels. So it was a very interesting use case that wouldn't have been possible to spot without a technology like ours. Then thank you for bearing with me until now. There is one more thing that I wanted to show you, which is linked to the effort of keeping it as easy as possible for our users, which is the Copilot. So the Copilot, as I mentioned, is where we are looking at the data completely from a non-technical perspective. So the Copilot can do quite simple things, such as everything that I showed you right now, select a specific month, and well, let's ask him what he can do. So, hello, how can you help me? He will tell us that he can help us with monitoring CO2 emission, explore emissions, which locations, select a year. So again, everything that I did so far. Let's ask a very simple question. So in 2025, what was the highest emission months? And it should tell me that June is the highest emission month. I can already see myself in the graph. So not necessarily I have to ask this question to the Copilot, but he can help me understand what is the highest emission. Now we have a bit of lag. I should try to refresh everything, but if you have any questions in the meantime?
Yes, there are quite a few. Let's take them straight away, I guess, because of the time.
Yeah.
So obviously, so let's start off. I guess Michaela asked, how do you transform the total column CO2 observed by the satellite in emissions and emissions by sector using surface measurements? So that was the question.
Okay,
Yeah.
that's it. You want to take it, Matt? I saw you muted.
No, I was just saying the non-technical explanation is that we have sensors on the ground in Dijon. We have 75 sensors that give us very hyper-local data combined with the satellite data. And then we have also computational fluid dynamics. So we're looking at how the emissions are moving in the city because it's a very turbulent environment. And so we can basically go from a concentration to a complete flux of emission and see how the air is moving the emissions and how they are also going into the atmosphere. So that's where we have some invested quite some time and patents into this technology. And yes, go ahead if you want to ask anything, add anything. Sorry, Lorenzo.
You gave a very good answer. I mean, we can talk about it's a very deep technical topic, and as Matt was mentioning, we dedicated a lot of time. So I would be very happy to go more into technical details if that's relevant for you, Michaela. Hope that I'm pronouncing your name well. So yeah, but this is a perfect high-level explanation to it, so nothing to add.
Are you happy with this, Michaela, or you want more technical depth?
I'm a researcher, so I would like to have more details, but I understand the point of our presenter, so we may leave it for another time.
Perfect. Okay, I mean, we can always, afterwards catch up. Thank you. Then the second, there's another question here that we want to consider, which is around like your sector breakdown. And I think the question is, how many sectors does your system currently cover at present? So you know, you mentioned transport, housing. So what's the sort of, how many of those sectors do you consider, and which ones maybe?
Yeah, so the sectors was one of the interesting topic that we worked on for SPACE4Cities, where we started to work with, so to give also a bit more technical details, we worked with a custom foundation model based on Terramind, which is the one developed from ESA and IBM. And in this foundation model, there is, of course, already integrated the land use, land cover, as it is called. So a map that will tell you what is on the ground and where. We started to work with this, but then we customized these and many other aspects in the foundation model to increase the granularity. So what we do to allocate sector is working with the foundation model enriched with OSM categories. We selected, we developed a pipeline that selects 73 different categories on the ground, and then we aggregate these categories in the sectors that you were seeing in the demo. This is a bit complicated way to say that we have a very granular understanding of what's on the ground, and we can aggregate it as we like. Okay, so you could even change some of the sectors if you wanted. Absolutely, and there is a very interesting aspect. Like we work, for example, with the port, as Matthew was mentioning, and they are interested, of course, in these different things with respect to cities. So we had to review the sectors in that case, and we work on completely different aggregation of the data. We are quite free and modular to do it.
And if I may, just to add one small detail. So this is Cabo speaking, Chief Product Officer at Ever Impact. One of the main focus of phase 3 would be exactly that, like working with the city, partnering with them, and trying to understand how should we categorize the grounds to develop those sectors and customize it for each city, depending on how they want to report those emissions.
Perfect. Clear. Thanks so much. Look, I think we've got some more questions, but at the same time, I also want to respect that everyone has a certain slot between the different companies. So maybe actually it's a question that we can bring anyway into the panel conversation, Peter. So yeah, just bear with me. So we've sort of come to an end now. Thanks again, Ever Impact team, Lorenzo, Mathieu, for presenting this, and Say to chip in. Yeah, so I hope that some of the other presenters are still there, and now is your chance as well to come online briefly at the end. So I could see Candela briefly coming in and out, but please join in if you would like. And I don't know, Denise, are you around still? We're also looking for Yanis. So yeah, thanks again for the nice remarks. Okay, so at least a few people here. So whoever obviously is there still left from the presenters, yeah, please turn on your camera and be there. Okay, so obviously this part is really just maybe to kind of look across some of your presentations and what you've done, and I think a good thing really is because a lot in the audience are actually cities and regions who have an interest in what you guys are doing. Many of them might want to, or are thinking potentially, how can I deploy this in my environment? What are the conditions or preconditions? Are there any things that if that I need, you know, on my side to make your solution work or run? So I want to explore this angle a little bit if possible, and maybe to better bridge this as well to like maybe Peter's question. So I will then maybe start last. Maybe I start with Ever Impact. I think Peter obviously had a remark around saying that the city of Dijon has 75 sensors, so there's obviously a requirement to get more granular data for your solution to work. And I think the question more is, I guess, deployment of ground sensors. A, is this a prerequisite for your solution? And B, what would be like the ratio look like, right? And or if you have any other sort of things to kind of throw into this, Mathieu.
Yeah, thanks. No, very good question, and that's actually the whole journey of Ever Impact. We started quite some years ago, about 10 years ago, and we managed to reduce the number of sensors. So Dijon was the first lab with 75 sensors where we've learned a lot. But now we are capable to deploy only a few sensors. So we've done recently Lausanne, Bern, and Zurich, only 3 sensors for those cities, because we have a good model from the existing sensors in Dijon and other locations. And we're also adding some satellite power as well. So the goal is to limit the number of sensors and make it very affordable and accessible to cities and reduce the barriers to adoption. Yeah, the more we go, the less sensors needed. And we are now moving from specific project deployment for cities towards building an infrastructure and actually working with cities in a more strategic manner, in the sense that the city of Paris, or the region, will deploy 50 sensors, but we're looking to equip another 10, 20 cities in Europe and start to have a global network. And we're also looking at Asia, and really start to have stations rather than specific sensors for a specific project, and build a network like that. So we're in a transition, but yeah, the less sensors needed.
Okay, perfect. So this means a solution, a city might also, your solution might also work without sensors in a city, but obviously if you have some, it would be obviously improving the sort of your tool at the end, the data it provides, correct?
Correct.
Perfect. Good. Yeah, let's maybe ask, let's go, Reda. So what do you need from a city? I guess you've shown you can import some data, but let's say, I guess your tool works without, right? Any additional data to start with, correct? Or
Yes. I mean, there's no need to import anything. Basically, what we need from a city is an operator who had a good grasp on what his problems are, what he needs to supervise, and the only thing he needs is a computer with a good internet connection. That's it, really.
Okay, excellent. But obviously, if there are some data sets available, you could leverage them. And what you would be looking for, or in the best case?
You see, it's always interesting to get more information at what you have. Yeah, if you have data on drought or flooding, the immediate thing you're looking at is where the water is going. Yeah, who's going to be compensated? But then, with the years, that water gets into the ground and is stored somewhere, and it starts to affect the infrastructure, the stability of the how do you say, the foundations. When you combine it with the satellite data, these things start to make sense, because you see where the water finally moved and what type of infrastructure it has affected.
Okay.
So combining is always interesting immediately, or to understand past events, for example. We did a lot of work showing that we identified in time when something started to be unstable, and it was easily coordinated with high precipitation at that time. So the water finally had an effect, and we could see where this effect was localized. So additional data contribute in more refinement in understanding what the history of that deformation, why exactly is happening. But also, of course, you always have a good start just with the satellite data.
Perfect. Thank you, Reda. Obviously, Candela, so what is your take on this? I mean, how about your solution? Obviously, you focused on, I guess, the sort of LLM that you kind of created over your tooling, but obviously, in order to deploy your tool overall, what are the assumptions that you have on a city?
I mean, let's say for starters, a city that doesn't have any kind of GIS solution on their own. So we have our platform with our agent. So we have the insert data, we have the meteorological APIs that give us all the temperature and precipitation data. So let's say we don't need anything, any data sets from the city to start with. We just need the people, so they use the agent to do uses and to understand what is needed from the city and how the agent can help you. Then when we have this city that wants to leverage the solution, maybe they have like what type of materials every asset is built of. So maybe the agent might be able to call. So we say, okay, this needs to be prioritized and is made of this material. So we can add more data. I mean, the more data we have, the better the results will be, but we don't need that to start with. And then we have the final solution, that is the city that has a digital twin or a city GIS. So in this case, we don't integrate their data. Through the MCP, they integrate CityMotion into their solution. So they have all the capabilities of CityMotion within their own GIS, and then they have plenty of information there. So it really depends what the city has, what they want to share, and how they would like to access the results.
Brilliant. Yeah, and Yanis, obviously, again, with CHERISH, what are the sort of things that you would require from a city, or what would make your solution better if you had it?
Yeah, thanks for the question. So it's a bit similar to the other solutions. We can start with a baseline with basically open data from OpenStreetMap. So there we just need to know, what is the municipal or the jurisdiction boundary you are managing, which I think is quite obvious. I mean, we can also simply say, okay, you are from Ghent. Let's take the entire Ghent metropolitan area limits from publicly available data. So we can start off with no more than this. And then basically we have two additional possible extensions, which obviously give you more and more insights and better experience. So level 2 is you have your own asset list with prior inspections recorded, etc. And the level 3 is you are already a kind of digital twin or smart city with your own building 3D models, which we can plug also into CHERISH and show you, as I showed in our demo with Helsinki, where to really focus inspection in the intra building level, like, where do you really go start inspecting first at the inside your building.
Excellent. Thank you. Thank you. So yeah, so in essence, I think what's great to see is that all solutions can actually be deployed without additional data required, just merely by the capabilities of your tool and obviously the satellite data that you get, or insert data that you get. But obviously, there's more value add if new assets could be brought in from the cities, right? So I think I can summarize it this way. Well, yeah, very good. One thing, obviously, I have to ask is, Mathieu, is like your ambition to deploy your own satellite, right? Which is sort of obviously quite aspirational. What does this satellite bring to the table compared to other solutions, right? That are already out there, the data that you can already access. So why would you need it? And what's the unique thing about it compared to what EU currently has?
Yeah, well, that's many questions into one. Well, it's all our story. We started in 2014 with NASA, who had launched the first satellite called OCO2, and they were looking for entrepreneurs to deploy sensors on the ground, and that's how we got the idea of Ever Impact. And it is now it was open data, but the data was quite, every month and a half, quite coarse, every 3 kilometers, not always in the city center. So we had to do a lot of rework. Fast forward 10 years now, we've always wanted to launch a satellite to really fix this issue and really bring proper data, because it's packaged into regulations and financial instruments. And it is now no more vision, it's reality. We got the funding for the first satellite, and we're working on the production. This summer, we start the production. And what it brings is really basically a way to scale to the world, and it's the best value for money. So avoids to have many sensors. It allows to calibrate, and the satellite technology is what's going to be the future of tracking carbon emissions, and we want to be a pioneer there. So
that means you will get rid of your ground stations.
Not completely. No. The goal is
Sorry.
to keep some, but to basically have the optimum number of satellite and sensors. What you need to understand is that if you look at current satellites, the companies invest about 150 million to launch them and launch a constellation. Here, because we're using ground sensors and small 32 kilo satellite, it's not that big, huh? We're looking at 20 million total to cover the globe and have a constellation of 10 sensors and about 10 satellites and 5,000 sensors. So we spend 10 years killing the cost to really make it happen.
Okay, good.
And maybe it's worth as well to mention what is happening currently on the rim of CO2 monitoring by satellite. So as Mathieu said, there is the NASA, so OCO2 satellites, and the Trump administration is decommissioning this one. So it's important also to provide to Europe a sovereign capability. Of course, there are like missions that are going to be deployed, like CO2M from the European Commission. But the issue remains the same. Even if the precision and the accuracy and the ground resolution is better than OCO2, it's still coarse, and we need to position ourselves in terms of complementary mission compared to the European Commission investments, basically.
Okay, thanks, Say. Thanks. Let's open the floor now to the audience as well. I mean, do you guys have any other questions? Now hearing all the presenters, anything that wasn't answered in the conversations before that you would like to ask our presenters? So again, you can use the chat, you can raise a hand. I guess after a 3-hour session, the minds are getting tired as well. So there is one by Peter again. No further questions actually. Good then. But he was inspired. Thank you for sharing this, Peter. Okay, brilliant. Yeah, I think for me, there's sort of one more thing that I would want to sort of like get out of you. That is like obviously quite a few of those cities would be potentially or regions that are part of the call or that are following us might apply for a replicator call, right? And is there, let's say, and they would also have to, if your solution will be one of the last 5, they will also obviously have to say what solution they would like to adopt and replicate. Like, I'm going to turn this the other way around. Is there a specific profile of a city that you would favor for a replicator pilot, or it doesn't matter for you? So maybe very quick one here, starting maybe with Radar this time.
That is a tough one. Yeah. I don't know. We try to adapt the solution to a large panel of possible replicators. We try to focus on the cause, the reason for the need of our solution, and it turns out to be quite the same one for everybody. The budget limitations, the staff limitations. You know, when you have to try to figure out how many assets to look at, and you have a limited number of people. You have to prioritize. How to prioritize? That's the key thing.
Yeah.
We had statistics showing that 90% of the time they went to see things that didn't need inspection.
Yeah.
So it's really waste of things. So
short answer, what will it be?
It will be if you are really overwhelmed, you know, you really don't want to fix things and you have a sense of urgency, then you are a perfect client for us.
Perfect. Let's go to Candela.
Yeah, I will say any city in Europe. I mean, we have full coverage of satellites. There is always I mean, the Earth is a living planet, so things move, and buildings sometimes have issues, infrastructure. So just be aware of what's happening in your city, because we have the data. So please go ahead and use it, and I'm pretty sure you will find interesting things.
Perfect. Yanis, any take on
Yeah,
this?
again, similar to the others, I would just add the dimension that you have some kind of an asset-centric work or view, like you're managing all the hospitals, all the schools, all the cultural heritages, or the churches. The power of our tool and our approach resides in the fact that at the end we focus down to an asset level logic. I think that's the relevant denominator here.
Perfect. And Mathieu?
Well, we have two categories, I would say, of cities. Of course, I would say in a passive mode, most cities are potential customers, and we'd like to work with you. But we also are looking to equip some cities with sensors. So I mentioned the example of Paris, very active in air quality and pollution and greenhouse gas monitoring. And we're trying to equip sensors with, we have a bit of financing and sensors we can deploy. And we're also trying to give a role to cities as an enabler and willing to contribute data. And by being a pilot test, you join a whole network globally and network in space with satellites. And so if you're more active and really committed, there's an even better role for you. So we're always keen to work with both, but anyone very motivated, always better.
Okay, excellent. I think there have not been any further questions popping up in the window. So I think I take now this opportunity to thank you all for staying with us. Obviously, first off, for joining and staying with us, but also for our presenters to take the time and really explain nicely what they've done over the last 6 months and more, obviously. And obviously, we're wishing you the best of luck to make it to the next stage. And and obviously, for everyone else, please join in tomorrow, same time at 10 for our Demo Day Part 2, where you will hear about the other 5 solutions. So again, thanks so much. A little applause. And I hope to see you guys tomorrow again in the next session. Have a great rest of the week.
Thanks. Bye-bye.
Bye.
Thank you.
Bye-bye.